Hello, my name is Larry Lapides. Together with my colleagues at Maymon, Shay Harari of NVIDIA Networking, and Lee Moore, as with myself from Imperas Software, we're going to talk today about RISC-V processor verification and present a case study. We'll start today by talking about the RISC-V processor design verification problem. We'll then talk about the verification flows, give an overview of different flows. We'll talk about RISC-V reference models, present a simple step and compare flow that we used, as well as a complex step and compare flow, the results, and then conclusion. So let's start by talking about the RISC-V processor DB problem. A good way to begin this is to talk about the evolution of the RISC-V architecture. So a little over 10 years ago at the University of California, Berkeley, the RISC-V instruction set architecture came into being. And over the next 6 years or so, it was further defined, refined, and there were some test chips made. And on the software side, there were some publicly available tests developed. At the end of that period, the RISC-V Foundation was formed to manage the RISC-V instruction set architecture and standardize the architecture, promote the architecture. The following 2 years saw a little bit more effort in RISC-V in the community. There were some proof of concept chips. Mostly these used minion processors, processors that were not exposed to users from the perspective of being able to program on those. So this was bare metal software that was just running on those chips, nothing external. And then the last 2 years have seen further increase in complexity, taking those minion processors and expanding those to IoT, SoCs, to microcontrollers, and now getting real-time operating systems and firmware running on these and actually starting to deploy some of these. And then starting this year, we're seeing even more complexity with 64-bit processors, with multi-heart, multi-core CPUs, with the vector extensions, with bit manipulation, hypervisors, debug mode. We're seeing these for application processors, which is actually what we're talking about here, and also looking at AI SoCs. And now the software has gotten, again, even more complex with Linux, Linux drivers, and AI compilers. And so this progression, this increasing hardware and software complexity, requires the use of best known methods for processor and SoC architecture, for implementation, for design verification, our subject today, and for software development. So if we look at the design verification problem and think about where RISC-V is and compare this to ARM as an example, ARM has stated that they run on the order of 10 to the 15th verification cycles per processor, which is about equivalent of 10,000 RTL simulators running constantly for 1 year. That's a lot. There's verification of the interface between the network on chip and the processor, and thousands of SoC designs with the ARM processors have been successfully produced. And there are similar stories for ARC and MIPS and Tensilica, these existing processor architectures. With RISC-V, the story is different. You want to ask, how well verified is an individual processor, whether from a processor IP vendor, open source, or self-built? How well verified is the interface between the network on chip and the processor, and how to deal with custom instructions and other features? So even if you're purchasing processor IP from a vendor and you feel confident in the quality there, you still don't know how many SoCs this has been in, how well verified the interface between the NOC and the processor is. What if you're going to add custom instructions to that processor IP? And then if it's open source or self-built, the problem is compounded. So now let's talk about verification flows that we've seen in the RISC-V community. Previous work on RISC-V uses primarily trace comparison flows. In this case, last year at DVCon, we presented together with Google and Metrics a paper showing one of these trace comparison flows with the Google open source instruction stream generator using the Metrics RTL simulation. And so here the test stimulus went into both the RTL and into the Imperas reference model. There were log files produced with the instruction traces, and post-simulation, after simulation, a comparison was done to make sure that the results were the same. Now, there's also functional coverage that's been added into that to see just the quality of the verification you're doing. The problem that we have here is that this flow supports only simple instruction tests. It cannot support asynchronous events, including interrupts and debug mode. The nice thing is that trace comparison is done post-simulation. It's actually easy to get started, but it is a bit inefficient in its use of simulation resources because you've got to go all the way through the simulation before you can determine that there's a failure in that specific test. So some of the previous work started talking about a step and compare DV flow, and that's shown here. There's going to be some sort of a stimulus that's going to get run on both the RTL device under test and on the reference model. And the idea behind the step and compare is to be able to handle those asynchronous events. It's for the device under test to actually be able to tell when an interrupt has happened, be able to tell the reference model exactly what's happened, how the interrupt is being handled. And then when they get to the end of the instruction retirement, then the comparison is done. So the comparison is done dynamically as well as being able to step and compare. So this isn't a lockstep. It's a step by the RTL and then a step by the reference model. So here the reference model is encapsulated into a SystemVerilog module. The whole thing is encapsulated into a SystemVerilog test bench. And the SystemVerilog module then talks to the test bench, and there can be introspection so that you can examine the state of the reference model, as well, of course, as examining the state of the RTL device under test. Here's a bit more detail on this encapsulation of the reference model. We see here that the DPI interface is used to connect the Open Virtual Platforms RISC-V CPU model to the SystemVerilog encapsulation module, and then SystemVerilog is the interface into the SystemVerilog test bench. In our project, we used parallel verification flows. We used a simple step and compare flow. The tools used in this were the Cadence Excellium RTL simulator, Cadence Specman verification environment, and the Imperas RISC-V OVP sim instruction set simulator. So in this case, combining the RISC-V reference model and the simulator. And this was used for verification of the basic instruction functionality. We also used a complex step and compare flow, again using the Cadence tools, but now using an Open Virtual Platforms RISC-V reference model, including support for custom instructions, and the Imperas MStarDev simulator. So these are now separate executables that are working together. And this provides better support, this whole flow provides better support for verification of asynchronous events and debug mode, among other things. So using parallel flows achieved optimal use of verification resources at the lowest cost. As we've seen in these past few slides, the RISC-V reference model is a key piece of the processor verification flow. So let's talk a little bit more about this. Let's start by talking about the requirements for a RISC-V reference model. The model needs to model the instruction set architecture, including all versions of the ratified spec and the stable unratified extensions. You need to be able to easily update and configure the model for the next project. You need to have it be user extendable for custom instructions, custom registers, also custom interrupts and events. With the openness of the RISC-V architecture, it isn't just instructions, it isn't just registers, but also the interrupt and event architecture that you might want to customize. You need to be able to model actual processor IP, for example, Andes, Sci-Fi, open hardware, Swerve, as well as anything you are building yourself. There needs to be a well-defined test process, including coverage metrics for the reference model. It needs to be able to interface to other simulators, whether SystemVerilog, SystemC, or even virtual platform simulator. Because the reference model might be used first for design verification, but you're going to use it for other things like software development. And while it seems obvious, it still bears mention that there is value in a common platform for verification and software development. And continuing that line, the reference model needs to interface to software debug tools, GDB, the Imperas tools for that, software analysis tools as well, interface to architecture exploration tools. So most of the RISC-V instruction set simulators on the market can meet 1, 2, maybe even 3 of these requirements, but not the whole range of these requirements. The Imperas models and simulators were built to satisfy this whole range of requirements, and these models and the simulators have been matured through usage on non-RISC-V ISAs over the last 10 plus years. Imperas builds the Open Virtual Platforms fast processor models. These OVP models are open source and free. The models are built in C using the OVP APIs. And then these APIs are supported by OVP Sim and the Imperas simulators. The APIs are available on the OVP website. They're publicly available. It's nothing proprietary. All of the models have both C and SystemC native interfaces, and the models are available under the business-friendly Apache 2.0 open source license. They do require an Imperas simulator license, either OVP Sim or one of the commercial simulators to run, but one simulator license is all that's needed for multi-core and many-core platforms. The Open Virtual Platforms library of RISC-V fast processor models includes models of the generic specification, so 32, 64-bit, and then the full alphabet of RISC-V extensions, as well as the privilege modes. The OVP library also includes models of the Andes, Sci-Fi, and open hardware processors. Custom features, instructions, registers, interrupts, and events are easily added by the user or by Imperas. These new features are added in a side file so as not to perturb the verified model. Custom instructions can be analyzed for effectiveness using instruction coverage and profiling tools. And custom interrupts and events can be added to all the spec flows and all the CSRs with priority and order consideration. So this is a key piece of flexibility in the reference models. Quality is also an issue, of course. These models are built using a test-driven development methodology where tests are built at the same time as features are added. There's a continuous integration test flow that is used with over 15,000 tests for the models plus the simulator. These tests are run every time an Imperas developer checks in code. We also use mutation testing to check the quality of the test suites internally. And there is additional testing by the processor IP vendors to validate the models. Configurability was a key requirement for the reference models. And here we show just an example of the different parameters available in the OVP reference models. There are more than 100 different parameters or overrides in the models. These include the privilege spec version, the debug configuration version, the bit manipulation version, vector version, the different instruction extensions, CSR configuration, clint and click configuration, also the debug configuration. So this is just an example of all the parameters that are available in the Open Virtual Platforms RISC-V models. As far as adding custom instructions, I mentioned that that was an easy and well-defined process. The first thing to do is to characterize the C application, because most of the time you are adding instructions to optimize a specific application. So first, characterize the application, develop the new custom instructions, add to the application, add to the model, add timing information, and then rerun the characterization and iterate on that. And when you're happy with that, you can optimize and document the model and then release and deploy. Here we're showing just some examples of adding custom instructions to a RISC-V model. In this case, these are encryption instructions. This is a fairly easy example that is shown here. So again, these are added into a new extension library, a side library, and not into the main piece of the model. One of the key things here is that when you do add the custom instructions, you do get those automatically showing up in the tools that you're using here in the debugger and also in the analysis tools, in this case, the trace. So let's look first at the simple step and compare flow that was used. So here we show this simple flow. This is using the Google instruction stream generator. Tests are generated on a per heart basis because actually we're looking at a multi-heart processor. And then those tests are run into the Imperas reference model and also into the Specman environment here. In this situation, this is similar to the trace and compare flow because the Imperas simulator is run separately from the RTL simulator. And then the Imperas results are added into a Specman scoreboard. And here's where the difference is, because then as the RTL simulation is running, it can compare on the fly these expected results. And so it is a step and compare flow. It's just that the comparison results are generated separately. So this again is used for just verifying the basic instruction functionality. Nothing really complex going on here. The RISC-V OVP sim reference model that's used has been available for nearly 2 years in the industry. Imperas has made this available. It's high quality, free instruction set simulator. Just download off of GitHub, implements the full RISC-V envelope, configurable for all features and spec, but it doesn't handle the custom instructions. One of the things that was needed here is to add in support for the bit manipulation instructions into the Google instruction stream generator. And here we show support for adding the bit manipulation instructions into the code, and then the test generation portion of that. So now on to the complex step and compare flow. So this looks fairly similar to the previous flow with the Google instruction stream generator generating the tests on a per heart basis. But now actually the RISC-V reference model in the Imperas simulator is run concurrently with the RTL simulator, with everything controlled by Specman. And then there's a comparison of register change after each command. And so again, at instruction retirement, we're doing this comparison. So again, it's the Cadence Specman and Cadence Excellium RTL simulator are used, and the reference model and the RTL device under test are stepped essentially in parallel, but the reference model can take cues from how the RTL reacts to the interrupt. And this flow enables the sync of the RTL device under test and the reference model for interrupts and both asynchronous and synchronous events. The encapsulation of the RISC-V reference model within Specman looks very similar to the encapsulation in SystemVerilog. Here, the C API to Specman was used. So this is effectively the same. It's providing a way to introspect the state of the RISC-V reference model dynamically. One of the other advantages to the concurrent simulation flow is that you can do interactive co-debug. So in this case, you see on the left the debug environment for the Cadence Excellium SystemVerilog simulation. On the right, the debug environment for the Imperas reference model simulation. Being able to set a breakpoint and have the complete simulation stop, both the RTL and the reference model, is great for debug, especially for asynchronous events. So let's take a look now at the results. First thing, I've talked a bit about the processor, but let's be a little bit more specific here. This is a RV64 IMACB with support for different privilege modes. So integer, multiply, atomic instructions, compressed instructions, bit manipulation, the different privilege modes, debug mode. There are custom instructions and also a custom interrupt scheme on here. For example, there are error events that are in here. Using the simple step and compare flow, we're able to do behavioral verification, or verification of the behavior of the simple commands. But this also includes being able to look at things that are not supported in the spec for the processor. For example, looking at floating point instructions as an illegal command. So we see that here we're able to look at the behavior. We're able to look at branch jump sequences. We're able to look at multi-cycle sequential insertion. We're able to get very high functional coverage for this. Moving on to the more complex flow, we see some very interesting cover points and actually across on here. This sort of complexity in the verification environment cannot be covered using the simple step and compare flow. And here we're getting very high coverage, in this case showing 100% coverage for most of these, because we're using this complex flow, because we're able to support the asynchronous events. So conclusions, robust, comprehensive, best known methods approach is needed for RISC-V processor verification. Step and compare methodology is necessary for verification of asynchronous events. And the key pieces of the environment include the high-quality RISC-V reference model, the ability to introspect from the test bench into both the RTL device under test and the reference model. And as always with DV, functional coverage metrics are important. Thank you very much.